Hi guys, I hope you hear me well. Today's topic is about the eventual consistency done right, a lecture you've chosen from the Patreon vote poll. And let's start. If you have any questions during the live workshop, you may ask them on the YouTube channel, which is on the right. And also, for those of you who are new around here, all the lectures are in English because I have an international audience from my YouTube channel, and some of the people who watch me there decided to join my Patreon, so they don't speak Bulgarian very well. I'm a little bit surprised from this topic because I recently held the same lecture in one of my soft tuning courses, but I guess it's an interesting topic, so we will do it again. What we are going to cover, we have quite a lot to do today, so I hope you are patient enough. We have to cover consistency between services and why that is an actual problem. Because when we have a normal web application and a single database, it's very easy to store data. And if there are some failures, for example, the database decides to time out, or the network fails, or whatever other reason to have a failure, nothing happens with our data because our data is either saved in the database or it's not. So it's quite simple because of the consistency which the database provides when we have a single database. However, when we have multiple services and when we have applications spread among many servers, usually these servers have separate databases. And with separate databases, it's very difficult to handle. It's more difficult. It's not very difficult, actually. You'll see in a minute. It's more difficult to handle partial failures. What will happen if one of the databases is unavailable and we have to save data from a business process which spans multiple databases? Then we will have one database with valid data state and another in which the data will not be saved, and that's a problem. So we need to make sure to cover all these failures and all these scenarios in which some of our databases is not working. Usually in a typical web app, that won't happen that much. Uh, for example, in our softuni.org application, which is built with microservices infrastructure with many databases, we haven't had a single failure since our launch 1 year ago, I believe. So it's a rare problem, but we need to handle it because if our application grows and if we have a lot of users, and for example, if we didn't scale very well our application, there will be a problem if one of these databases fails. So we're going to talk how to how to resolve that problem, that issue, by first introducing the problem itself, why it happens, and how to communicate between services. Because usually we have different kinds of communication which we may use when we are using the microservices approach. The typical solution involves the so-called message broker. There are multiple message brokers available. One of the most popular is RabbitMQ, so we're going to use that in our code. When we introduce the message broker and when we start saving our data correctly, then we need to handle these partial failures, eventual partial failures. First, we have to make sure that if for some reason the message broker is down, we're going to see that in some sort of a scheme in a minute. If the message broker is down, we need to handle that. And then if the database of the other service is down, we need to handle that too. So we actually have to implement two solutions, one for the message broker and one for the database and the server. So what exactly is the challenge? First, microservices approach becomes very popular because a lot of the giants in the IT industry started using it because it's easier to scale an app when you have for example, millions of users. For example, Amazon, for example, Netflix. And a lot of people started using microservices even though they don't exactly need them. But nevertheless, it's a very popular approach, and we developers tend to like to do what is cutting edge and what is a hype currently. And currently, microservices are a big hype. So we need to handle all the challenges because with microservices we get quite a lot of benefits. We can split different servers to different teams, for example. We may have independent deployment, independent development. The benefits are quite a lot actually, but there are a lot of challenges, and the main challenge actually is this eventual consistency. So if you understand how to handle eventual consistency, you may consider yourself that you can do microservices good enough. So what will happen if we have, for example, a catalog microservice which maintains information about products? If we imagine a normal e-commerce shop, an e-commerce shop, for example, like Amazon, when we have you may have a lot of products in a catalog, and when a user decides to buy something, he needs to put that product, and we as developer needs to put that product information in a shopping cart. In a typical microservice approach, we may decide that the catalog and the products are in a separate server and the shopping cart is independent from that server. So we have two databases and two servers. One database to store the products themselves and one database to store the shopping cart information. So in the first microservice we have information about our products, for example with the price, and in the shopping cart microservice we need to have our chosen products from the user and the price. So in both microservices we need to store the price data. When a product price is updated because of a promotion, because of various business reasons actually, an administrator will go to the app and will change the price in the catalog. But that change needs to be propagated to the shopping cart microservice because the user needs to see that the price is now updated and he will pay more, for example, or less depending on the situation. So this is a fairly easy scenario if we have a monolithic application. If we have a monolith with a single database, that's pretty much a piece of cake. Every junior developer can do that. It doesn't require a lot of knowledge because all you need to do is you need to fetch the product from the catalog for the products table, and you need to fetch the current shopping cart, find all the shopping carts which contain that product, and then update the price with a single transaction. That's completely fine, but with microservices, even though that business scenario is quite common, we have a lot of what will happen if the shopping cart microservice is not available or the database is currently not available for various reasons, networks, timeouts, whatever. We have a problem because if we update only the price in the catalog, the shopping cart will not have the updated information, and of course that's a problem. So the typical approach developer who is not familiar with microservices patterns will decide that HTTP is perfect and it will be completely fine to create something like that. We have a client here, C for a client, we have the catalog with the products, and we have a shopping cart. So when the client decides to update the product and the price, so decides to add $5 for the price, the developer needs to call the other service too. The developer needs to update that price here in the database here. So one of the initial solutions, if we're not familiar with eventual consistency and all the patterns behind it, we may decide, okay, the client will call this one, and then after it gets a response which confirms the product is updated, the developer may decide that the client will need to call the second server and will wait for a response. That's kind of a okay solution. It will work, and if the client is not does not receive a response because this microservice fails for some reason, the client may retry. So it may try to update the product information in 1 second, in 2 seconds, in 3 seconds until it succeeds. That's fine, but there's a problem when the user decides to close the client. Then the retry will not occur and we will have unstable data, because the data here will be valid, but the data here will be not. And according to this typical situation, this is not a solution. The client should not call multiple microservices. It should call only one, only a single microservice, and then this microservice should be responsible to send the data to the service here. Now, how to send it? We may use REST API and HTTP. The problem with REST API and HTTP is that we essentially have the same issue, but this time on our server, because what will happen if this server does not respond? If this server does not return a response saying everything is fine, we've updated and now the data is consistent, what will happen? And it will be a problem, because if this response is not returned right away, this product microservice, the catalog here, needs to wait for a response, which may take, for example, 10 seconds. And for 10 seconds, we need to wait these 10 seconds for this response right here. So the client will need to wait 5 seconds for the whole operation if one of the microservices fails. And that's not very convenient in terms of a user experience. Also, what will happen if this product fails while it's waiting for the response? It's again an issue. We cannot handle both failures at the same time. So that's quite a challenge, and we've seen that the typical and the straightforward approaches will not work. The HTTP solution from the client or the HTTP solution from the server. So we need to use something more convenient, and that's an event-based communication, the so-called publish-subscribe pattern. So if you hear or read somewhere about the publish-subscribe pattern, they are talking about this. They're talking about what we are going to cover in this lecture. Another solution which I didn't show is if we have the microservice calling the database directly. So we have one database with the products and another database with the shopping cart or the basket in this example. We may call the database directly, but then we don't follow the separation of concerns principle, and that's a problem because this catalog microservice starts depending on multiple databases. What will happen if we have another microservice here with another database which we need to update, for example, orders information or whatever, customer support. It can be literally anything in an e-shop, in an e-commerce environment. So what will happen if we need to call multiple microservices, 4, 5, even 6? Then this catalog needs to wait for this database, for this database, for this database, and quite a lot of databases actually, which are quite a lot of dependencies. And with this solution, we are going to build a monolithic app which spans on multiple processes, which again is not our solution. We want to have independent microservices, because what will happen if we need to migrate this database? If we need to migrate the baskets table or the shopping carts table, we cannot deploy the baskets microservice independently from the catalog microservices. It will be quite we need to deploy everything at once, and if we need to deploy everything at once, then we essentially have a monolithic application with quite complex infrastructure because we separated the services. So calling the separate database is not an option. Calling an HTTP request also is not an option, because again, if we have, sorry about that, if we have multiple microservices, this one, another one here, and if we need to update all of their databases, if we need to call this one, and this one, and this one, we will have, for example, 1 second of 1 second for a response. It may be a smaller value, but if we consider scaling our application, if we consider that this application may be used by millions of users, 1 second is good enough. So 1 second here, 1 second here. So the catalog microservice needs to wait for 5 seconds before responding to the client, and that's a lot. So to keep it short, we won't be able to scale our application very well if we decide to use HTTP, because it needs a response. We need to wait for it. Or if we decide to call the database, an external database, because we need to wait for a response. And all of these responses add up to a bad final value. So what we can do is we can do the so-called asynchronous way to send messages, or the publish subscribe pattern, by using events. And this synchronous way, which uses HTTP, is essentially an anti-pattern, because the client calls the basket may need to call the ordering may need to call the catalog may need to call something else, and if this fails, this needs to try again, needs to retry the call, which may take 5 seconds. So we may have again 10 seconds or more for the client to receive a response from the basket. This is synchronous communication, and it doesn't scale well. It may be fine if we are living in a perfect world, in perfect environments where nothing fails, but typically when we have a cloud solution, or when we have a lot of nodes, a lot of microservices working together, then we have failures, partial failures. So handling them will be easier with asynchronous messages. For example, the client sends a request to the basket microservice, and that's completely fine. The basket microservice updates its database and sends a message, hey, this database was updated and the product price, which has an ID of 5, for example, is now $10. So you need to update your price too. And then it returns a response. So the basket microservice doesn't wait for a response. It just sends a message and expects that message to be delivered in some point in the future. So this is why it's called eventual consistency, because we don't need to expect a response. We just send a message, and by using an infrastructure which guarantees us that this message will going to be delivered at some point in the future. If, for example, this fails, this message will be pending in our queue of messages, and it will be delivered right away when the ordering microservice is restarted. So we can be sure that even though we're going to have 5 seconds of delay, the message will be received, but the client will not have to wait. The client will receive a response, hey, everything is fine. And this message will be in such infrastructure that it will guarantee that it will be delivered at one point in the future. So that's the best scenario, to have AMQP, which is essentially an event bus or asynchronous messages query protocol. This is the solution. This is the solution we are going to use in our code. So the problem is not about the protocol, the HTTP, even though I already showed you a lot of drawbacks if we are going to use HTTP. So the protocol is not the problem, but the coupling and the style of our messages is more the problem. So the more coupling we have, the more difficult is going to be for the developers, for the deployments, for the DevOps operations, for literally everything. Almost everyone I know who used the microservices approach made the same mistake I already showed you. When I first started using microservices a couple of years ago, I used HTTP. All of our colleagues were not familiar with microservices patterns, so we used HTTP, and we had a lot of problems. We had a huge disaster because the network response for even simple operations like update the price in a product, the example I've used earlier, we had a lot of problems, and the network latency was it was not responsive. It was not a production ready app, so our infrastructure was failing a lot. So we need to handle all these partial risks, all the failures, and there are common patterns which solve the problem, so we are going to cover them. I already said that the HTTP is popular because the whole web is built around HTTP, and it's very simple. So when we can, in which situations we can use HTTP, where and when actually HTTP requests are quite acceptable. First, when we have a client to microservice communication, because browsers typically use HTTP, so that's completely fine. When our client app calls the microservice, that's completely fine. Also, we may have the so-called API gateway. The API gateway is essentially a facade between the client and all the microservices. We may have products, orders, shopping cart, and instead of calling all of these microservices directly, we may decide to put a gateway between them. The so-called API gateway is just a server which handles all the incoming requests from the client. The whole purpose of this gateway is to have a single point which the client can call. So the client code becomes much easier to maintain, and the gateway we then call all the other microservices. So the client may only call the gateway, and the gateway may call the other microservices. This gateway pattern is not necessary, but in some situations it's preferable because it may contain cross-cutting concerns like authentication and authorization, because the gateway may contain this logic for authentication, and this way we don't need to copy the authentication logic everywhere. So the gateway may save us from cross-cutting concerns. The other benefit of a gateway is to have a single point of external infrastructure. We may put all these microservices on internal networks, and the external world will not be able to access them. So we have a smaller area of hacking purposes, for example, a smaller area in which different hackers or different external users may try to sabotage our application. So the API gateway has its purposes, but it's not necessary. It's not something we need to consider in every microservice architecture. And the other HTTP request which is acceptable is from API gateway to microservice. But when we need to call a microservice from another microservice, then HTTP tends to bring a lot of problems, a lot of latencies, a lot of timeouts, for example. So it's not a good approach. Trust me, I've seen it live on a production site. Even though it's easier to handle, it's very easy to make an HTTP request. You need what, 2 lines of code or something like that, and it's done. So the pitfalls of the HTTP are blocking and low performance. I already showed you that, so our scalability is quite impacted. We have HTTP coupling on our business level, which should not happen. Our business logic and business services need to make an HTTP request to an external service in order to perform an operation. And if we follow separation of concerns in our design, in our infrastructure, and in our application code, we should have non-web related logic on our business level. So our service layer needs to have only and nothing else but normal business logic. And failure is very difficult to manage. Failures occur. Partial failures are very common. For example, if a hosting provider gives us 99.9% of uptime, if we have 100 microservices, then that means that for 1 or 2 hours every month we will have a problem with our app, and 1 or 2 hours are quite a lot. We need to prevent this. Of course, failures may still happen, but we need to make sure they're at their as possible minimum as we can do. So we shouldn't rely on request response if that's possible, and in microservice to microservice communication that is possible. When we need data from different microservices, we may duplicate it. That's absolutely okay in the microservices world. We can duplicate data without any problem. The only problem is to have the same data on all the duplicated places. So that's the solution we're going to cover in a minute. Then if a microservice needs to invoke an action in another microservice to do a business operation, we need to do it asynchronously. Asynchronously means we send an event and we say, hey, the price has changed. Please update your database. And that's it. We don't need to wait for a response. Waiting for a response here is a pattern for a big disaster. So we can use any protocol to transfer data, but we shouldn't have synchronous dependencies. Synchronous dependencies in a simpler language means we shouldn't wait for a response. We just need to fire and forget. That's the solution here. We fire an event, we make sure that the event is actually fired, So the infrastructure received, the queue we're going to use received the event, and then we forget about it. Our infrastructure should guarantee that the event will be delivered at some point in the future. That's the aim here. That's we're all about. That's what we're going to do. So asynchronous messages are the way to propagate changes throughout multiple microservices. So if we have multiple databases in our application, we need to use asynchronous messages to propagate these changes. This is called the eventual consistency. Eventual consistency, it means that at some point in the future, it may take 30 seconds, but we don't care. At some point in the future, the data will be consistent. You may have noticed such behavior in some of the popular apps, for example, Facebook, for example, Amazon, or any other app which is very popular. You update a data you own. As a user, you update something, but it takes, for example, 2 to 3 seconds for that update to occur on various places in the website. So this is essentially eventual consistency. Your data is saved, but it may need additional seconds to be updated everywhere. Usually it happens in less than a second. It's not that slow, but when a partial failure occurs, we may have to wait a bit. So the microservice just sends a message. It fires an event with some header metadata and a body with the data the other microservice may need, and do not expect a response. Don't expect a response at all. So if a service needs to return a response, sometimes you may need to return a response, then you send another asynchronous message. So if you need to have a response, you don't wait for it. You just forget about it and don't block the current request. You return to the client everything is fine, and in the near future the data will be updated. So these asynchronous messages use asynchronous messages queue protocol, AMQP. That's the solution here. There are various solutions in the .NET world, but that doesn't matter. We're going to use the most popular ones, which are Mass Transit and RabbitMQ. Of course, you may find another library or another message queue, or you may change the infrastructure, but the pattern is the same. You need to do the same thing we're going to do here to make sure that you're doing eventual consistency right. So the infrastructure is a lightweight message broker, RabbitMQ, or you may use Azure Service Bus. AWS also have a solution. The Google Cloud platform also have a service bus. Essentially, what you need is a message queue or a service bus. It's the same. There is no difference. So if you search for popular message queues or popular service buses, you will find various solutions. The RabbitMQ is, I believe, the most popular currently. It's very mature and it's very easy to set up and use. And the rules, again, HTTP for client plus API gateway plus first microservice level. This is completely okay if we want to use HTTP, but if we want to use backend communication, microservice to microservice, we need to use asynchronous message queue protocol. This is the correct way. So this is a scheme which describes exactly what happens when we need to communicate between different microservices. This is the event-driven communication with multiple receivers. With a single receiver, it's essentially the same, so it doesn't matter. So a client calls a microservice, in this case a user profile. This is a typical Web API HTTP exposed microservice. This microservice needs to update the database. So what it does is it updates the database, it sends the SQL needs to update the database, or it may not be a SQL, it may be a MongoDB database or any other non-SQL database, it doesn't matter. It saves the data in the database and fires an event to the so-called event bus, service bus, message queue is the same. This is an infrastructure which guarantees that if it receives a message, it will be delivered sooner or later. So if for some reason this is not available or this microservice is not available, the event bus or the RabbitMQ in our case makes sure that sooner or later, it may be in 30 minutes, it doesn't matter for the RabbitMQ, sooner or later the message will be delivered. So as soon as the basket microservice is again live and is restarted, our event bus will guarantee that the message will be delivered. So we're going to use an infrastructure which guarantees that if it receives a message, that message will be delivered on every other microservice. So that's the case we want to do here. Again, the steps are: we receive a request on one of our microservices. This request saves the data in the database and sends a message to our service bus. The service bus guarantees us that this message will be delivered. So when this message is delivered, the database will be updated here and of course here. So if something is down, the service bus will wait for it to be back online so that it will deliver and send the message. How to use a message broker? You need to go to rabbitmq.com if you decide to use RabbitMQ. So RabbitMQ, you need to hit get started, download it, install it, it doesn't matter. The installation is very easy. It doesn't matter which operation system you're running, the installation will be super easy. You may need to install Erlang too, but the installer will tell you download it from here. It's a next installation. It's very easy. You can configure the default port and user access. You can configure it. You can add an administrator, a password, but for development environment that doesn't matter. If you decide to use a cloud-based solution, you will need to configure the solution to have an administrator or a password or a user or whatever it gives you. When we are using a development environment, RabbitMQ is installed locally, so we need to access it by calling localhost. If we go to our services after installation, if we have RabbitMQ with a running status, then everything is fine. So currently, RabbitMQ infrastructure is up and running, and I can easily send messages to it by using for example, 3 lines of code, 4 lines of code. It's very easy to send a message. There are NuGet packages which allow us to send a message. Then what we need to do is install mass transit. We may install the official RabbitMQ client package, but it's more difficult to set up. It has quite a lot of options. It needs more knowledge, so to speak. And usually you don't need to configure the RabbitMQ that much. What you need is a simple way to send a message and to receive a message. And mass transit is an abstraction which serves that purpose. So what we have here is the same code I used in one of my courses. It's a car rental system which has a lot of microservices. It has an administration web server, dealers web server, identity web server, schedule web server, and statistics web server. All of these have separate databases if they need a database. If we go to our databases, we will see that we have 4 databases for this application, for the statistics, for the authentication, for dealers, and so on. The whole idea behind that application is that dealers can register in our app, car dealers. These car dealers can publish ads for car renting. So as a dealer, I can, for example, put Volkswagen Passat for renting for $40 a day, for example, or something like that. So the dealer's microservice has that logic. It has a dealer's controller, a typical HTTP API controller, which serves the details of the dealer, dealer ID, creating dealers. It's nothing very special. Essentially, one dealer needs to be a user, a registered user, and it needs to provide a name and phone number in order to be considered a dealer. Then we can add car ads if we're a dealer. We need to be an authenticated user who marked himself as a dealer, and we can search car ads, we can create car ads, we can edit, and so on. It's quite straightforward actually. We find the dealer, we find a manufacturer, for example BMW, and then we create the car ad. That's the action we are going to use in our eventual consistency solution. Then we have the following problem. We have a statistics microservice which just saves statistics. It saves all the car ads which were viewed by the users, and it saves the total car ads in our system and total rented cars in our system. But both of these are using separate databases. So when one of my clients decides to add a car ad, it sends a car ad here and we save it to the database. We need to have a way to save the same data on the statistics microservice. We need to say, hey, a new car was created. Please update the statistics. And if we don't have that solution, every time a dealer adds a car ad, the statistics won't be updated. And again, we said that HTTP is not a solution. One possible solution here is to have the client calling the dealers and then calling the statistics, but this makes the code on the client harder to maintain. Also, if the statistics are not available for some reason, if there's a partial failure here, the client needs to retry the code to the statistics. But what will happen if the browser is closed because the user saved the car ad and closed the browser? Then we won't be able to retry the call. That's a problem. Again, the same thing may happen if we decide to make an HTTP request here, because this HTTP request requires a response. And if that response takes 5 seconds, the client will have to wait 5 seconds to receive your car was created, a message from our system. So it's not very convenient, it's very blocking. And if we have a more complex business operation, it may need to call a lot of microservices. And if it has to call a lot of microservices, then this value here may become 15 seconds. It's blocking and non-scalable. This is why we need to use eventual consistency. Our client creates a car ad here, and we save it to our database. We fire a message in our RabbitMQ instance, and directly return a response to our client saying your car was updated or your car was created. Thank you. Then the RabbitMQ infrastructure guarantees us that sooner or later this message will be delivered. So sooner or later the statistics microservice will have the eventual data and will have eventual consistency. It doesn't matter whether it will be in 2 or 3 or 5 seconds because we are not blocking the client. The client received an information that everything is fine with his request. So everything was saved. So the statistics microservice needs to save the data to the database too. So we're going to use a message. Of course, with this infrastructure, we may have another problem. What will happen if the RabbitMQ fails? What will happen if the infrastructure, the service bus, is not available? We won't be able to send the message. So essentially, that's again a problem. We're going to cover that in a minute. Let's first solve the problem which makes our let's first solve the problem that we don't want to use HTTP for this call here. We want to use something else. We want to use asynchronous protocols. So this is what we are going to do. But first, we are going to make a 5-minute break so we can I need a 5-minute break. So in the 5 minutes, I will be back. Okay, guys, let's continue with the actual implementation of the whole theory I talked about earlier. So what we need to do is we need to install these two packages. First, we need to install Mass Transit. Mass Transit is an open source tool which has quite a lot of options actually. It has a lot of service buses available, so you may not use RabbitMQ with Mass Transit, you may use Azure, for example. It covers the most popular service buses out there. Also, it's very easy to set up, literally 10 lines of code which you can copy from the presentation. I created the presentation so that it will be like a step-by-step guide which you may follow if you decide to try this. I'm going to link the presentation and the source code on Patreon so you can download it, play with it, clone it, whatever you like. Okay, so first things first, we need to install those packages. What I like to do when I have multiple servers, I like to extract a common project like this one, which is a simple class library containing everything which is used by all the servers. So a single server startup class becomes something like this. Add web service with this DB context and this configuration and app.useWebService. I extract all the logic here, all the common logic. I extract it to the separate project so that it will be easier to be reused. If we open the statistics, startup, it's essentially the same. Add web service with another DB context and another configuration file and use web service with the current environment. Of course, all the configurations are different. For example, the statistics server uses car rental statistics database and the dealer server uses car rental dealers database. But the setup code is essentially the same. And if we open the common project infrastructure, service collection extensions is essentially the all the common cross-cutting functionality we need to add to all our servers. For example, add database, add application settings, add token authentication, add controllers, which comes from the MVC, add automapper, and so on. And here I have different kinds of methods which help me achieve what I want. For example, this registers the DB context with the default connection string. This registers some application settings. This register the token authentication, which is just a copy-paste code from the JWT authentication documentation. Some automapper configuration, whatever. So if I want to add messages infrastructure, I'm going to say I'm going to add another iService collection. Service collection, add messages, and here I'm going to extend by using C# extension methods the services collection coming from the ASP.NET Core framework. So add messages is a method which I'm going to call in each microservice which is going to send messages. I am going to go to the dealers microservice and I'm going to say add messages. Then in the statistics microserver, again, I'm going to say add messages. Obviously, in every microserver in which I'm going to use messaging and event bus and the whole concept we are talking about today, I'm going to use the add messages method because it will be reused across different services. Okay, so first things first, I need to install ASP.NET Core. mass transit for ASP.NET Core, and I'm going to install it in the common project, and then I'm going to need to install mass transit for RabbitMQ. If you want to use something else in the documentation, you can find it very easily. Then the RabbitMQ. And both should be installed in my project. Then what I need to do is a little bit of tricky code. It looks something like that. Services at mass transit. On mass transit I need to save the so-called consumers. These consumers I'm going to talk about in a minute about them. I need to add a service bus. That will be the bus I'm going to use for sending messages. A service bus is created very easily by calling bus.factory.create using RabbitMQ, and then I need to provide the RabbitMQ configuration. Currently it's on localhost, but if I have a port, if I have a user, if I have a password, I need to provide it here. And then I need to add all the consumers. These consumers, we're going to talk about them in a minute. And lastly, in order for the mass transit infrastructure to start working, we need to call add mass transit hosted service, because this only registers our message consumers and setups our RabbitMQ, but it doesn't start processing messages. So in order to start that, we need to call as mass transit hosted service. So what I need to do is add mass transit, then I'm going to say mass transit. This is copy pasted from the documentation. You don't need to remember the whole code. You can copy paste from the presentation too. So I'm going to say use mass transit and register a service bus from RabbitMQ, because that's my infrastructure. Then what I need to do is I need to say what is the host of the RabbitMQ. I can provide the host from the app settings configuration, from Docker Compose file, from whatever. Actually, it doesn't matter. For now, I'm going to provide the string here, but of course, if we need to use a production environment and settings and so on, it should be like we have the connection strings, for example, application secrets and other things, but I'm not going to do that because it will need more time. You can provide the username here, the password. You can provide the username, the password. You can provide everything here, so it's not a problem if you have an authentication configured on RabbitMQ. For now, I'm going to keep it simple. Next thing, before we continue, we need to say at mass transit hosted service. We also need to configure our consumers, but we're going to do that in a minute. So pretty much that's it. That's everything we need to do to make mass transit work with our RabbitMQ. We need to provide the connection string and the port. Usually a RabbitMQ connection string contains the username, the password. You can set up it directly from the connection string. Let me, for example, this is a connection string for RabbitMQ instance. User, 2 points, password, at our host, port. We may have a virtual host, it doesn't matter. Different kinds of connection strings are completely acceptable. So you can configure it the way you prefer. Cool. So this is everything we need to start mass transit, but for now we don't have any messages, we don't have any logic which consumes these messages, because on the receiver end we need to provide logic for message processing. But first we need to create a message. In our case we have a car add created message. So the whole idea is I need to have the following. Mass Transit provides me a very easy iBus interface which will publish our messages. This interface will publish our messages to the RabbitMQ infrastructure we're using in our code. So it's very easy. What I want to do now is when I create a car and save it to the database, I want to say await this publisher dot publish, and I need to provide some message here. Pretty much that's it. I need to provide the message I want to publish to all the other microservices. So let's create a message, because the message class will be used by both the dealers and the statistics microservice. The message class should be in the common project. So I'm going to create messages and I'm going to add a folder dealers, because that's a message coming from the dealers microservice. That's not necessary, but I like to put my classes very well organized so that I can easily find them later. And I'm going to create a class which is car add created message. It's a good idea to put the message suffix to the class name, because this way you can recognize that this is part of the event-driven communication. Also, usually when we create classes for our events, they're in past form. Car add created, car add updated, car add deleted, dealer created, and so on. Car add viewed, primero. So you can put whatever you like here. This is just some sample data which we're not going to consume because we don't care about it, but just for an example, you can put whatever you like. You can specify the car add ID which was created, the manufacturer, a model, price per day, whatever you prefer, because the other microservice may need some of the data. Okay, so I created the message, and the next thing I need to create is the so-called consumer. The consumer is a special class which implements the iConsumer interface coming from Mass Transit and specifies what kind of message it handles. So if I create a class which implements iConsumer of car add created message, this means that every time somebody publishes a car add created message object, this logic here will be invoked. So Mass Transit guarantees me that for each message which is of this type, it will be handled by this class here. So what we need to do is we need to decide where we need to handle the message. Handling the message should be done in the statistics microservice, so I need to go there and create messages. Again, the same structure. I'm using the same folder because it will be easier for developers to recognize that this folder is about event-driven communication. Then I'm going to say, okay, let's create a new class, and I'm going to say car add created consumer, like this. Here I need to say iConsumer. Let me wait for ReSharper to wake up. iConsumer of the message I want to consume, and currently I want to consume the car add created message. This way, I create multiple messages for the different business operations, and I create multiple consumers to handle these messages. And this consumer should be very simple. What I need to do is I need to update the statistics in the database, but I have services for that. I have iStatistics service. So what I need to do here is I need to say, okay, at car at. I want to say we want to update the statistics and we want to add a new car ad which was created by some dealer in another microservice. Then I'm going to implement that. All my services which contain only business logic and nothing else usually inherit data service, which just provides me an easy access to the DB context used, and it has a save method which updates or saves the entity in the database. So what I need to do here is I need to get the statistics from the database. Var statistics equals await this dot data. Give me the statistics set from the data. Essentially, give me the information from the database. I'm going to put async here. And then I'm going to say statistics dot first or default async. Statistics dot total car ads add 1 because we want to update the data, and then I'm going to say this data save changes. Please save the changes, and that's the business logic here. Of course, we need to have some no checks if statistics equals no, throw some no reference exception with some sort of explanation message and so on, but that's not our concern in this demo code. So this will be more than enough. Good. Then I need to go to the carrot created consumer, and it supports dependency injection. So I can just say, give me the statistics service, inject it through the constructor of the class, and use it in the consume method. The consume method will be invoked every time a new message is received. And you can get everything here. You have quite a lot of information. When was sent, the source address, some request ID, message ID, some headers. You have a lot of information. Usually you would like to get the message. The message is essentially the data we sent. You can see that it's from the class we created earlier, car add created message. If we go here, and this is our class. Good, so what I want to do here is I just want to say await this statistics that add car add and mark the method as async. It's super simple. It's very simple. As you can see, we just created a message class, we just created a consumer for this message, and said, every time I receive a car ad created message, please add one car ad, because this means that the car ad was created. Of course, you can do something like this. You can provide the car ad ID to check whether this car ad was added already in the statistics. You can do a lot of business logic, which but that depends on the case. I want to keep this as simple as possible because I want to focus on the event-driven communication and not that much on the business logic itself. The business logic depends on the app, but if we consider the messages, it's super simple. It will get a little bit more complex in a minute, but it's very simple to get started. Just register the services, which are a copy-paste code from the documentation. Just specify where is our RabbitMQ, which is very easy to obtain. If you're using a cloud, it will give you host and everything else you may need. You create a message when you need to send a message in the car ads controller, and then we just need to publish that message. So if I want to publish the message, I need to say car ad created message, and I can pass all the information I want to pass. I can say car ad ID. I want to say manufacturer is car.manufacturer.name, model is car.model, and price per day is car price per day. So I sent all that information, and everyone who consumes this information will use it in their part of the business logic. It's very simple. The only thing we're still missing is that nobody currently knows that we have a consumer class. We created it, but nobody registered it in mass transit. So this won't work for now. If we don't add our consumers, they won't work. So to add our consumers, what we need to do is we need to say in our mass transit registration, I want to add a consumer and I want to register it in the RabbitMQ. It's a bit tricky to remember all of that, but nevertheless. So what we need to do is we need to say we're going to do it like this. I'm going to get parameters of types which are going to be my consumers. I'm going to specify these consumers in the startup file of each server. Here I need to say for each consumer I want to say add consumer like this. Then in the RabbitMQ part, for each consumer, I want to say RabbitMQ receive endpoint, and here I need to provide the name of the consumer. What I'm going to do is I'm going to provide consumer.phoneName, because I'm going to use to say that I want to have the full name of the consumer, because if I have multiple consumers with the same name throughout my microservices, I will have a problem, because by default what happens is mass transit creates different queues, Q1, Q2, Q3, and so on. And we have the servers here. So when mass transit publishes a message, it sends that message to a specific consumer, to a specific queue, sorry. So if we want to send car add message, it adds them to this queue, because this is the queue for car ads. This is the queue for dealers. This is the queue for statistics, for example. We essentially create a different queue for each message type. And when we create a car ad queue, if we don't specify the full name, and if we have a consumer here and a consumer here, the default behavior is that this message will be delivered to a single server. This is a problem, because this message may be needed for 2 servers or 3 servers. So this is why we register our consumers with their full name, which the full name essentially means that my name of the consumer will be the namespace dot the class name. So each consumer, if it has a different name, will be a different queue. This way, if we send a single message, mass transit will deliver it to all the servers. This is why I'm using full name here. Then I need to configure the endpoint, configure consumer, and I need to specify the current context which comes from here. That's again from documentation. And then I need to provide uh, the consumer type. This way I registered my consumers and I specified that I want to use these consumers in the RabbitMQ instance. It's essentially the same code from here. I just repeated it, but we could have copy pasted it, but that doesn't matter. This is important because if you put the name of the consumer here, that's a problem, because if you have the same consumer names among microservices, you will not receive the message in all of them, and you will receive as a first come first serve. Imagine that if you don't put the full name here, is the same like you and your neighbor have the same post box, and when you receive a letter, there's a chance that your neighbor will see it first and get it, so you won't be able to get your letter. So it's either the neighbor or me who will get the post messages, and that's kind of a problem because we want to have two separate post boxes and everyone should receive their messages and their letters. So this is why I'm putting the full name here. That's pretty much it. If we try, let me start the projects. I'm going to start the statistics, dealers, and identity because I need to be an authenticated user to send messages. Let's start that and see if everything is working correctly, because there may be a bug. So running the app, waiting for everything to fire. All the servers are live. What I'm going to do now is I'm going to create a car ad. I already have an registered dealer, so I'm going to put this authentication token. This is a simple JWT authentication, and I'm going to try to save this this car right here. But first, I'm going to call the statistics server to see how many cars currently there are in the database. It's on 5005. I get and I've configured the ports of each service in the properties launch settings. For example, the dealer starts on 5001, the statistics starts on 5005. Okay, so let's go to the Postman. I'm going to call the statistics server and I'm going to see that I have currently 14 cars in my database. So what I want to do right now is I want to create a new car in one server, which is on 5001, and then see whether the other server was updated. So I'm going to hit send here. I received 200 OK, there was a new car, and if I hit statistics, it's not working. So we don't have eventual consistency implemented yet, I guess, because I forgot something. And it's very important, but nevertheless. So what I have right now is I have the consumer service here, but nobody knows about it. If I go here, I will see that nobody knows about this consumer. In a simple language, mass transit doesn't know that I have a consumer. So a message was sent to the RabbitMQ, but nobody was there to receive it. If there was no exception with the logic here, the message was sent. The message was sent, but there was nobody to receive it. So what we need to do right now is we need to register our consumer. If we take a look at our service collection extensions, what we did is we receive consumers here and we register them, but I never registered my own consumer class. That was my mistake. So what I'm going to do, I'm going to go to the startup class of the server who wants to consume a message, and I'm going to say add messages, type of, and I'm going to say car add created consumer. This means that I now told mass transit to have that consumer right here. So if I start the app, it should start working because now mass transit knows about the consumer class and it should invoke this method right here. I'm going to put a breakpoint so that we can see what happens. Before publishing the message, I'm going to put a breakpoint here, and before consuming the message, I'm going to put a breakpoint here. This is to validate that our infrastructure is up and running. We can see that there was a message here, and if I take a look at the message, I will see that the car which was created is now received, which is very interesting because we now experienced the partial failure thing. Because what happens with RabbitMQ? RabbitMQ stores the message, and if nobody receives it, it tries again in a minute. It's not a minute, it tries again. Then if nobody receives it, again it tries again, and it retries a couple of times before it deletes the message itself. If nobody received the message, then it should be deleted, but the initial configuration is that if nobody received the message will be received in the future. This is essentially the eventual consistency we were talking about. So if we imagine that our car add controller sent the message, but the statistics server was down, so nobody received it, we are currently handling partial failures because the statistics, when it's again up and running, mass transit and RabbitMQ receive the message and process it. So I'm going to hit continue, and we can see that now we have 15 cars. So even though we had a partial failure, a fake partial failure, because it was actually my mistake, but you got the point. There's the data was updated 30 seconds later, but it was updated. We had eventual consistency, and we didn't have a blocking operation right here because the car was created, a message was sent, but it was received later in the future. But nevertheless, we have eventual consistency and the data is stable. So even though I updated one of the databases, the next one was updated later and everything is now fine. My databases are in valid state. Even though for 20-30 seconds they were not, it doesn't matter because once the app is live again, the message will be received, and that's the cool thing about this pattern. Let's try again. Let's see what will happen if I decide to add the same car. I will hit send. We can see that it's saved in the database and then the message will be published. I hit continue and the message is received. It's essentially the message I just sent. Here it is with the new car add ID. So if I hit continue and go to the statistics microservice, I will see that the car add was again updated. So I have a synchronous way to communicate between these two microservices. They don't block each other, and that's a pretty cool thing. Of course, we can use other methods, for example, gRPC, but gRPC is kind of too new, so we may consider it when it becomes more mature. For now, asynchronous messaging is good enough. With gRPC, we will get a better performance, but in my opinion, we should wait for at least 6 months or 1 year more until we start incorporating it, because it's very new in the ASP.NET Core world and it may have some unexpected bugs, for example. Good, so we added eventual consistency, but there's still a problem. Before we talk about the problem, I would like to give you how to make messages more resilient. You can add the following configuration. You can set how many messages should be processed at the same time. By default, it's the number of CPUs available, but you may lower it, for example, the number of CPUs, half of the number of CPUs, so that not all CPUs process messages. There should be available CPUs for requests, for example. So it's a good idea to put a lower number than the default CPU number. Then you can use message retry and say I want to try 5 times every 100 milliseconds. This is useful when the RabbitMQ is not available, because what will happen currently, if the RabbitMQ is up and running and everything is fine, if we send a message, even though the receivers may be down, the RabbitMQ guarantees us that the message will be received, exactly like we saw earlier. But what will happen if the RabbitMQ is down? That's a problem, because we cannot send the message initially. So that message will be lost. We will see an exception. We will save the database. Imagine the following code. We save the database, but then RabbitMQ is down, so the publish never happens. Nobody sends the message, and this will throw an exception. So that's again a problem, because we handled the issues with failing services and databases, but we still don't handle the issue with failing RabbitMQ, and the RabbitMQ failure may occur. So we need to handle that too. So the first thing we can do is we can just go to the infrastructure, and we can say we want to have, let me stop the apps. We want to have the following retry policy. Prefetch, because I have 12 CPUs, you may use, I believe, environment CPU cores. I forgot the command. Let me search for it. .NET Core number of CPUs. The number of CPUs, environment processor count, not CPU count, processor count. Yeah, I'm not very good at what's the problem here? I'm not very good at remembering stuff. So I'm saying use an int. Oh, it's a U short. Environment processor count. Ugly stuff. Very ugly stuff. You may put that value in the app settings too. For example, different servers may have different CPUs, so you may put that there too. It doesn't matter. Then we say use message retry and try 5 times with this interval. Every 100 milliseconds, try to send the message again to RabbitMQ and throw an exception after these 5 times. You may put a higher number, for example 10, or you may try every half a second. There are no perfect numbers here, but 5 tries every half a second is more than enough. If the RabbitMQ is unavailable for a moment, this will work. But what will happen if RabbitMQ is not available for 5 minutes or more? If there's some problem with the infrastructure which we need to handle manually, then this will fail. So we need to save ourselves with failed messages, and that's essentially the next pattern we are going to use, because if RabbitMQ fails, these messages will not be delivered. And that's a problem because we are updating database but not the messages. So we're going to use the Outbox pattern. I'm going to take a 5-minute break again, and then I'm going to explain what the Outbox pattern is, how to solve the Outbox pattern with mass transit, RabbitMQ, and our infrastructure in the .NET world. And there we have it. Eventual consistency will be done, and we are going to handle all the common risks with that data processing. So again, 5 minutes, and I'm going to show you the Outbox pattern. So let's continue and let's solve the final piece of the puzzle, because we need to handle failures of the event bus itself. We need to have a mechanism to send messages even after the event bus is down, and when the event bus becomes back online, we need to restore these messages. So the Outbox pattern solves that. What we need to do is described here, essentially step by step. We need to create an additional table in the database, which will hold all the events or the messages in our system between microservices. And before publishing to our event bus, we're going to save the event in the database too with a local transaction. What that means is that when I try to save the car ad, I'm going to save the message, and I'm going to use a transaction so that if the car ad is saved, the message should be saved too. It's either both of them or nothing. That's the important part. So if we store in our database the car ad, we should store the message too. That's the important part here. So if we have something changed in our database, the message should be stored forever, just in case. And we need to store the event as pending or published or not processed, whatever the wording is. Then we're going to publish the event or the message to all the other microservices, and if the publishing is successful, if the publishing does not fail, we're going to mark the event as completed afterwards. So essentially I'm going to store the message with the carat in the database, then I'm going to mark the message as completed if the publishing is successful. Then I'm going to set a background job which will check every 5 seconds, for example, for failed pending events, and I'm going to publish them from the background job. This guarantees me that if the event bus is not available, all the messages will be stored in our local database as pending, and when the event bus is back online, our background job will get these messages and publish them for us. So even if RabbitMQ is not online, everything will still work fine. Of course, we need to save ourselves from database failures, but that's just entity framework configuration. We can say to entity framework that if a database failure occurs, we can retry it, but that's not part of the eventual consistency. It's not part of the event-driven communication. That's another topic. Something else, because sometimes we may have duplicate messages, because when we store them in the database, we may publish them, but before we mark them as published, the background job may get them and publish them twice. So we may have duplicated messages, which again is not a good idea. So what we need to do here is the receiver microservice should do one of the following. First, it may make sure the operations can be performed multiple times without affecting the result. And the other solution is to recognize duplicated messages and discard them. So recognizing messages is very easy. We can just add a GUID to the event and we can mark the GUID as resolved on the receiver end. RabbitMQ and Mass Transit have some message ID built in already, so you can use that. But the better way is to send messages which are not, which does not affect the result if they are duplicated. For example, the message should be something like, please set the price to $50, which if duplicated, it will be again $50. It doesn't matter. but it shouldn't be something like add $5 to the price, because if we send a second message, then it will become $10. So this is something we should consider when we design our messages. Our messages should be idempotent. So if we duplicate them, it won't matter. Here is the updated diagram, which shows how our new system is going to work. The catalog microservice will update the product and at the same time will insert the message in a table. The table will contain the ID, the event type, event body, state, and so on. The product table does not matter, but what's important is we need to store both these entities in a transaction. Lucky for us, Entity Framework uses a transaction on each save change call. So if we have multiple entities which we need to update and a single save changes call, we will have a transaction, so that's easy. Then we need to set up a background worker who will call the database every 5 seconds and will try to search for messages which are not yet processed. If it finds them, it will publish them. This way, even if the event bus is not available, eventually these messages which are not yet processed will be added here. How to implement that? First things first, we need to create a global message model. A global model which will be stored in the database. So I'm going to the common project, and in the data folder I'm going to add another entity framework model which will be called message. We're going to store all the information needed for this message to be published. Essentially, that's everything we need. I'm going to show you this in a minute. So we're going to store the serialized data as a field in the database, and we're going to save the data we are sending between messages as JSON. It's a field, that's important. Then we are going to have a message ID. We're going to have the type of the message, which is carat created message, carat updated message, carat deleted, and whether it's published or not. What's important here is to JSON serializer settings to say that we don't want to serialize no values, because if we have no values in our messages, this will throw an exception, and in this case we just want to ignore no values. We don't care about them, and I'm going to add new JSON serializer settings with no value handling to ignore, like this. Then I need to create a configuration, entity framework configuration, for this message model in the database. It's the same like all other models. Identity type configuration, and I need to provide what's the key, whether it has an index, and so on. So I'm going to say I want to implement this, and it's from message. Here it is. I'm going to show you that in a minute. Essentially what I do here is I say the message in the database has this ID. Then it has a property serialized data, which is not the default convention of entity framework, a public property, but it's a field, because I want to store the JSON data as field and use this one to deserialize it. And then I want to say the type has conversion, because entity framework does not work with types by default, so this is how I store it. I store it as an uh, I store the name of the type, and when I get it back from the database, I just get the type, which is the C# type, for example, carat created message or something like that. This is again copy-pasted code, which you can use as is. Finally, what we need to do is we need to create a base DB context which will contain the messages table. So I'm going to create that. I'm going to say, okay, I want to have base DB context, which will be abstract. And in this class, I'm going to add everything about the messages. This DB context class. We have the table messages, and I'm going to add a property configurations assembly because each different server needs to provide its own configurations classes. For example, for the carat database. And that's pretty much it. I'm going to say find the message configuration, register it so that you will register the message table in the database and apply all the configurations specified here. And this base DB context is going to be used by every DB context in my solution, which needs to have the messages table. So I'm going to paste it here. I'm going to implement everything missing, which is essentially the following property, and I'm going to say assembly get executing assembly is the current assembly from which you can find the configurations. So I'm saying get all these configurations for the database and use them. I need to add a constructor in the abstract class because otherwise it will not work. Protected base DB context like this. And my dealers DB context now will have the messages table. I'm doing this abstract base class because I don't want to copy paste this logic everywhere and this logic too. This is the whole reason. You can copy paste it, of course, but it's more difficult to maintain. Then in the statistics DB context, I'm going to say the same thing. I'm going to say use the current assembly to find the configurations you're going to need. Then let's rebuild that. And what we need to do right now is we need to add migrations for our new database messages. So I'm going to the dealers server, and I'm going to call add migration messages table. And this one. And if everything is fine, I should have a migration for the messages table, which will have serialized data, published true or false, the type as a string, and the ID. Good. And in the statistics microservice, I'm going to call the same migrations because I need the same table there. Done. It should be okay for now. So the next thing we need to do is we need to store the messages in the database. So what I'm going to do is all my services which use the database inherit from data service, and they have a save method. So what I can do here is I can change this class to have methods for saving messages. I can say something like when you try to save an entity, give me messages if you have If you have messages, give me them, because I want to save the entity and the messages at the same time. Then I'm going to say mark message as published, or just, yeah, okay, that's a good name. And I'm going to get the message ID here. Now I need to implement this logic. Let me add the params messages, and it's very easy. We just need to say this data dot set for message at message. That's it, and we have a single save changes here, which will guarantee me that if the entity is saved in the database, it will be saved with the message. Good. Then I need to implement the other method, which is mark message as published, which is a simple task to do. I need to find the message, await this data dot set from message, find me the message with the message ID. Then I need to say message dot published equals true. What I can also do is I can go to the message model and I can add mark as published, or just publish, doesn't matter, which will just say this dot published equals true. I believe it's mark as published. I believe this is a better name, because publish is like send it to the event bus, but mark as published means mark the message as published. Good. Yeah, this one. So I'm just going to say dot mark as published, and I'm going to call this data dot save changes. So I'm going to mark the message as published. Then what I need to do is I need to set the background worker, but before that I'm going to need to update the logic. I need to save the message, so I'm going to say message data equals the following code. This is the message data. Then I need to store the message in the database, so I'm going to say something like this. I'm going to say public message object data. I'm going to say something like this. Every time you try to set the data, set the type too. So save the type of the data, create carat created message, for example, and then serialize it. And here I'm going to say this data equals data. What I also need to do in order for entity framework to work correctly, I need to add a private empty constructor. That's an entity framework requirement, so this is why I'm adding it. Good enough. Let's go to the controller now, and let's say the message for the database is this new message. And this is its data. Then save the car ad and save the message too. Save both of them. Then try to publish it. If this fails, the message is saved in the database, so later on it will be still published. So if RabbitMQ is down, we are storing the message in the database. And if it doesn't fail, if it works and the message is published, I want to say car ads mark message as published message.id, like this. So mark it as published if it's correctly published. So if RabbitMQ fails, this works. This works. If everything fails, the message will still be persisted if the car ad is persisted. So we're going to have eventual consistency sooner or later. Good. What we need to do is we need to install a background worker. Hangfire is good enough, so I'm going to the common project and I'm going to install Hangfire. Hangfire is a background worker which allows us to execute background jobs. I believe I didn't install the core package, so I'm going to do it. And Hangfire ASP.NET Core. So if you are using another database, use something else. You can use Quartz, which is not Hangfire, which is a different library, but it does the same thing. Hangfire is good enough. It has support for SQL Server, for PostgreSQL, for various databases. So it's a mature product which works very well. We use it in softuni.bg, which is a site for the site was online for maybe 8 years now, so it's pretty stable. Good. You may register the Hangfire dashboard if you want to have an UI for the Hangfire dashboard, but that's not a requirement. Then what we need to do is we need to copy this from the documentation. This is exactly the first thing you are going to see, the same code, literally, the same code you're going to see when you open the Hangfire documentation. So I'm going to add everything. The only thing we need to do is we need to provide our connection string to the database in which Hangfire will live. So I'm going to add the application configuration here, and I'm going to say configuration.get connection string default connection, like this. Because I use the same connection string like in the database, in the SQL Server database here for the regular database, I may extract that, but we are not going to do that because it's a constant which is essentially the same, so we need to reuse it. It's better to reuse it and not copy paste it. For example, we can say something like this: private const string default connection equals default connection, and then we can reuse the string. That's better in terms of clean and high quality code, so it looks better and it's a single point for this value. Finally, before we finish with the Outbox pattern, we need to implement the background worker. It's very straightforward to do. What we need to do is we need to create messages hosted service. A hosted service in ASP.NET Core is a service which runs in the background. Hosted service, like this. We just need to specify what happens when the service starts, when the app starts, and what happens when the app stops. When the app stops, we don't want to do anything, so I'm going to say everything is fine. For the start async, we need to register a recurring job to occur every 5 seconds by using hangfire, and this job will call our database and publish all pending messages. And that's pretty much it. I know it's a little bit difficult if you see this for the first time, but take a look at the code or look again at the recording and you will get it. Good. Let's add that. And what we need to do is we need to register the service. We need a recurring job manager. This will be my job manager. I will need an instance of the DB context, but because messages, all hosted services are singletons by default, and the DB context is a scoped service, we need to get it in a little bit different way. I'm going to inject the iService provider. You see what I'm going to do in a minute. And I believe that's pretty much it. To register a service, we just need to say the following. This job manager dot add a new job, which will be called messages hosted service. Execute this method every time. The method should be public void, otherwise it does not work, so I'm going to mark it as public. And this is a cron job string. If you're not familiar with cron job strings, just search it on Google and you will see what it means. A cron job string essentially means a repetitive time frame. So the following string says execute the job every 5 seconds, every minute, every hour, every day of the week, every year. So every 5 seconds, no matter the minute, the hour, the year, the date, and so on, execute it. This is what it means. But you can generate your own cron jobs. Cron job, let me check this. You can edit it online and it will tell you what will happen. For example, if I say it will execute 1 minute after the job is scheduled. If we say it like this, it will execute every 10th minute. If we say it like this, it will execute every half an hour. If we say it like this, it will execute every minute past every second hour. So you can play with that to understand, but the whole idea is that the first symbol marks the minute, the second marks the hour, the third marks the day, and so on. And here I'm just saying every 5 seconds execute this method here. And this method is super straightforward. Just says get the message from the database, publish it on the event bus. Be careful because the publish method is asynchronous and this is not an asynchronous method. So in order to work correctly, you need to call getAwaiter.getResult. That's important. And then we mark the message as published and we save the changes. So I'm going to inject private read-only ibus, the publisher, like this. And then I'm going to get the DB context instance and using var data equals this service provider dot create scope, otherwise it may not work. Get service DB context. Then I can just say var messages equals data dot set, give me all the messages which are not published. Then I'm going to say for each message, not this to string, for each message, I want to publish the message. But I need to give the message data and the message type. So I need to say send the data and the message is of this type. And I'm going to say get awaiter dot get result, because this is an async method and we need to await it. But in order to await it in a synchronous method, we need to say get awaiter get result. Then I'm going to say message dot mark as published, and then I'm going to save the changes to the database. So I'm going to mark the message as published here, and I'm going to call the database after each successful publish, because I don't want to get 10 messages, then publish them and mark them as published afterwards, all of them, because if some of the publishing fails, this will not work. It's better to save every message which is processed. So this should be it. So if we didn't introduce a bug or something, some problem, this should be everything about eventual consistency. So let's start it and let's see what's going on. There are some errors, and the error is that I don't provide the configuration here because Hangfire needs the database connection string, which comes from the configuration. So if everything fires, we should have there's already an object named messages in the database. That's because I'm going to delete all the databases, because from my previous code before the lecture the databases were updated. So let's remove that. Let's rerun everything to see whether it will work. And I'm going to need to register a new dealer if everything works, of course. Cannot open car rental dealers. Okay. Nothing was created. So what I'm going to call here is I'm going to comment out this messages hosted service for now, because I want to migrate the database. Cannot open database requested by the login. Okay, let me check what's going on. All the databases were added. So if I restart the messages hosted service, it should start working. The problem was that I had already the messages table because before the workshop I tested that everything is working correctly to prepare for the lecture, and I didn't delete the database. So now we should have the databases correctly installed, and we need to try to populate the data again. We can see that Hangfire added some tables because it uses SQL Server. We can see that we have the messages, which everything is empty for now. And let me go and create a doer. First, I need to register a user, which has some data here. This is the token which I need to use for creating a doer. I'm going to create a doer with some name and some phone number. I'm going to say that the doer has the following authentication token, so this should create the doer. And then I need to create a car ad with the same doer, so I'm going to paste the same connection string. If we call the statistics, there shouldn't be any cars because we deleted the database. And now I need to save the car ad. Good. Everything should be fine for now. I'm going to open the messages, and I can see that the messages are stored in the database with the car ad. We have the car ad created message, and it's published with its data. So this message is published because currently the system works correctly. So now let's fake a failure. I'm going to hit a breakpoint here, and I'm going to save the car ad and the message in the database, but I'm going to stop before the publishing, like if the RabbitMQ is down or something like that. So I'm going to hit send, and then I'm going to stop the app. This essentially imitates failure of the publishing. And if we go to the messages, we can see that we have two messages now, and one of them is not published. And this is where our background worker will hit in and will try to publish the message. So I'm going to put a breakpoint here so that we can see how it finds the message and publishes it. At least that's the point. So let's wait a bit for the app to fire. And we can see that it found the message I sent earlier with the ID 2, and it tries to publish it. Good, so the background worker constantly checks for not published messages. If I try again, I will see that now everything is published. And if I go to the statistics, we should have two cars added. The first one, which was successful right away, and the second one, which had a RabbitMQ failure. So essentially, that's the eventual consistency pattern done right. This is the best way to use eventual consistency between microservices without any common failures, just using a service bus, in this case message RabbitMQ, and using the Outbox pattern, which has a background worker and a separate table for all the messages. A better approach, of course, will be gRPC, but I still believe that it should be weighted because it's quite new technology. A better approach in terms of having faster message delivery. You still need to store the separate data. You still need to have a background worker to publish that, but you will skip the event bus infrastructure and it will be faster because you will not use an event bus. Event buses are not bad or slow or anything like that. gRPC is just a little bit faster. So it's better at some point to upgrade the system to use gRPC, but the principles should be exactly the same. A background worker and a separate table to send messages which fail. So guys, this was pretty much it. We covered a lot of stuff for eventual consistency. It's a good knowledge to have even if you are not working with microservices currently, because when you need to extract a microservice in the future or when you start working on a new project which uses the architecture, you will remember that there's the thing called eventual consistency and there's a pattern to implement it right. There's a question. If you have any questions, you can write them on YouTube or if you watch this recording later, you can add a comment below the Patreon. One of the question is, are you sure Hangfire supports cron jobs under 1 minute granularly? I think it doesn't, not a big deal, but to prevent errors. We have used Hangfire with cron jobs below 1 minute because I believe it works correctly, because when I researched what to use in our system at Softuni, we decided to use Hangfire. And Hangfire has an extra cron job symbol. If you take a look at the normal cron jobs online, you will see that they have one less symbol. This is why, because Hangfire supports seconds. Cron dot minute, day, weekly. This is an old school to specify a cron job. I believe it supports, but I will check that because I may have some wrong information. But I believe it supports that because when I researched it, this is essentially the same code we use in Softuni and it didn't fail so far in a production environment, so everything is fine. But I'm going to check that additionally. Good. Any other questions? I hope you liked this lesson. It's super advanced in my opinion, but since it was voted, I decided to choose it. I'm going to post another vote for the next live workshop during the beginning of August, and hopefully it will be as interesting as this one. If you have any questions, you can also ask them in the private group I linked in the Patreon, so feel free to ask. Otherwise, thank you for watching, and I really hope you liked the topic. Good. Bye for now.